Hey everyone, welcome. Today we're going to pull back the curtain on the planet's hidden engine, this huge invisible system of air currents that pretty much dictates our weather, creates our climates, and, shapes life as we know it. This is the story of Earth's atmospheric circulation. But first, let's kick things off with a little bit of a planetary puzzle. Have you ever just looked at a world map and noticed something kind of weird? All the world's big deserts, the Sahara, the Arabian, the Gobi, the Australian outback, they all seem to fall in these neat lines like bands wrapping around the globe. So why is that?
Yeah, that is no accident. It's not a coincidence at all. The key to solving this whole puzzle is found in the air that's constantly moving all around us. The atmosphere, it turns out, holds all the secrets.
So, to crack this puzzle, we're going to break it down, piece by piece. First, we'll look at the Earth's big heat problem. Then, we'll check out the convection engine that tries to fix it. After that, we'll dive into the three-cell system that organizes it all, see how the planet's spin throws a wrench in things, and finally, we'll put it all together to see how we get our climates and biomes.
All right, first things first. We have to understand the one fundamental issue that drives, everything. The Earth gets heated unevenly. Not every part of our planet gets the same dose of sunshine, and that creates a massive, massive imbalance.
Think about it like this. Because the Earth is a big old sphere, sunlight doesn't hit it all the same way. Down at the equator, the sun's rays are like a laser beam hitting straight on, super intense, super concentrated. But as you move towards the poles, that same amount of energy gets smeared out over a much larger, curved area. It's way less direct. And that simple fact means the equator gets way, way more heat than the poles do.
So here's the deal. If all that heat just stayed put, the equator would get hotter and hotter, and the poles would just freeze solid. Not great, right? So the atmosphere acts like this giant planetary air conditioner, constantly working to move all that extra heat from the tropics up towards the freezing poles. But how does it actually do that?
Okay, so how exactly does this massive planetary AC system even work? Well, the engine behind it all is actually a super simple idea from basic physics. It all comes down to one word: convection. You've seen this a million times, right? When you boil a pot of water on the stove, the hot water from the bottom rises, cools off at the top, and then sinks back down again. The atmosphere does the exact same thing, just on a mind-bogglingly huge scale. Hot air at the equator rises, and cold air at the pole sinks. This simple circular motion is the absolute foundation for all of our weather. Now here's where it gets interesting. If the Earth was just a stationary ball, we'd get one huge simple convection loop in the north and one in the south. Easy. But of course, our planet spins. And that spin complicates things, breaking that simple loop into a much more elegant system of three distinct cells. And this right here is it, the tricellular model. You can see that in each hemisphere, that one big loop is broken into three smaller ones. We've got the Hadley, the Ferrel, and the polar cells. This is basically the master blueprint for how air moves around our entire globe. Let's take a look at each one.
We'll start with the big one, the real powerhouse of the system, the Hadley cell. Right at the equator, you've got all this intense solar heat warming up the air, which makes it expand and rise way up into the atmosphere. All this rising air creates what we call a zone of low pressure.
So as all that warm, moist air goes up, it cools down and it can't hold its moisture anymore, so it dumps it as tons and tons of rain. That's why you find all the world's great tropical rainforests right along the equator. But what goes up must come down. That now dry air gets pushed towards the poles until it's cool enough to sink, right around 30 degrees latitude. This sinking air creates a zone of high pressure, and as it comes down, it warms up and sucks all the moisture out of the ground, leaving clear skies and almost no rain. And bam, there's the answer to our puzzle. All the world's major deserts are lined up right under this zone of sinking dry air.
Okay, so what's happening in between? You've got the Ferrel cell, and you can almost think of it like a gear that's being turned by the two powerful cells on either side of it. It's not really driven by heat itself, it's just caught in the middle.
This is the cell that sits right over the mid-latitudes, where a lot of us live. It's basically dragging warm air from the deserts up towards the poles and pulling cold air from the poles down towards the equator. And because it's caught in this constant battle between warm and cold air, it's why our weather can be so, all over the place, unsettled and unpredictable.
And finally, up at the top and bottom of the world, you have the polar cell. It's the smallest, the weakest, and it runs on a really simple cycle. Super cold, heavy air sinks over the poles, creating high pressure, and then that frigid air flows back towards the warmer parts of the planet along the surface. So we've got these three cells moving air around. But there's a catch. The air doesn't just go in a straight line north or south. Nope. The Earth's spin throws a major twist into the mix.
This twist has a name, the Coriolis effect. And it sounds complicated, but the basic idea is that because the Earth is spinning under everything, moving objects, like a pocket of air, get deflected. In the northern hemisphere, they curve to the right, and in the southern hemisphere, they curve to the left. It's actually an illusion, but it has very real effects.
Okay, the best way to wrap your head around this is the old thrown ball analogy. Just imagine you're standing on the equator, where the Earth is spinning super fast, and you throw a ball straight towards the North Pole. Well, that ball keeps the eastward speed it had from the equator. As it travels north over ground that's moving slower and slower, it gets ahead, and its path appears to curve to the right. This is what creates our big, prevailing wind patterns, like the trade wind.
All right, time to put it all together. We've got the heat imbalance, we've got the 3 convection cells, and we've got the Coriolis effect twisting the winds. Let's see how this incredible system creates, well, our world.
This chart really lays it all out, doesn't it? It's like a cheat sheet for the planet. You can draw a straight line from the Hadley cell's low pressure at the equator to rainforests, and its high pressure at 30 degrees to deserts. The Ferrel cell's mixing zone gives us temperate forests, and the polar cell's cold, dry, high-pressure system gives us tundra. The cells literally architect the world's ecosystem.
And you can see this play out so clearly in the real world. Just look at Africa on the left. You've got the lush Congo rainforest right on the equator, and the bone-dry Sahara Desert just to the north, all thanks to the Hadley cell. And then you zoom out on the right, and you remember this is just one piece of a giant, interconnected global machine that's always in motion.
And get this whole system isn't just an Earth thing. Take a look at Jupiter. It spins way faster than we do, which creates a crazy strong Coriolis effect. This just shatters its atmosphere into tons of circulation cells, which we see as its famous colored bands and stripes. It's the same physics, just turned up to 11.
So there you have it. This amazing, finely tuned atmospheric engine is what distributes heat across our planet and creates all the different climates and biomes that make it so livable. It's an incredible system that's all driven by heat. So that leaves us with one last really big question to chew on. What happens to this whole system when we start to turn up the planet's thermostat?